today is basically, next week we will have the last week of lectures. I would suggest the following. There's a pretty extensive tutorial in the net for next Monday. And I would strongly suggest you look at this and you solve this. And then we would have on Tuesday another lecture. And I would offer, instead of having a lecture on Tuesday, having another tutorial. And I can put a set of questions in there covering basically everything we did. You can look at this then as a small test exam or whatever, and then we can talk about and discuss anything which might be unclear. I hope this is a reasonable suggestion. So then with this we would only have today's lecture and the lecture on Tuesday, and Monday and Friday we would use it for tutorials. Okay, what I would like to tell you today is, since we talked already quite a bit about metal-carbene complexes, I would like to continue a little on this. And especially I would like to focus today on diazo compounds which are very often used for generating carbenes. So the idea of having a diazo compound which in some kind of ways can generate a carbene by loss of nitrogen is one very common way. However, diazo compounds have another of other interesting features, and that is immediately clear if you write resonance structures here. So for example, in a diazo compound, you have an anionic carbon which is the equivalent, or which can react as a nucleophile with typical electrophiles. And I will show you a few examples of this. And then moreover, this structural feature can also, or is also a 1,3 dipole. And so it can undergo typical cycloaddition chemistry. If I want to show this, I can do this, for example, by writing a resonance structure of this type. So very versatile compounds which are therefore widely used for quite a number of different processes. And therefore, I would like to give you some more information on how to use them. And I would like to start in telling you actually how to prepare them. And this is already sometimes not so easy, or the chemistry itself to make them is easy, but you have to be careful. And you have to be careful because diazo compounds potentially are explosive. And I will show you 3 different types of diazo compounds, and you will see that you can stabilize them by putting substituents on here which can delocalize this negative charge. Then the compounds, the Azo compounds, become more stable and therefore are not as explosive. Nevertheless, you always have to be careful because nitrogen is an excellent leaving group. It develops then gas, and so therefore, if that happens in an uncontrolled way, explosions can result. So let's look first at the most simplest compound. Let's look at diazomethane itself. And for diazomethane, you always have to prepare it. It's not commercially available because transporting it would be too dangerous. But there are a number of compounds available which you can buy and from which you can easily generate the diazo compounds or diazomethane. And the common structural feature all these commercially available compounds have is that they are N-methyl, that they have these N-methyl nitroso unit in there, and then typically a reasonable leaving group. So this is something you can buy. It has a rather lengthy name. If you give the rational one, it's N-methyl N-nitroso paratoluene sulfonamide but if you buy it from Aldrich, it's simply being named as diazalt here. And what you have to do is you treat it, or you hydrolyze these compounds with base, and this way diazomethane is generated. Typically, you do this, you have aqueous base, you do this in an organic solvent such as diethyl ether. You have two phases, and as you hydrolyze this compound, the diazomethane will go into the ether phase. It's a yellow compound, so you can also clearly see that it has been formed. But again, this diazomethane is so easily extruding nitrogen that you have to be very careful. For example, you cannot have any rough surfaces. So that is why you do not prepare diazomethane in a normal flask where you have joints which, as you know when you work in the lab, have a rough surface area. So usually what you do is you take simple glass beakers. You want to take new ones which have not been scratched before a lot, so that there you don't have rough surfaces. And you also want to make sure, and we will see this, that the nitrogen is especially easily extruded if any metals are present. So you also want to be sure that your flasks or your beakers are very clean, and for sure that there is not for some reason any metal contamination present from anything previously you have done. So typically you use new beakers here, and then this works. There are other compounds available, like this urea derivative I write up here. This is N-nitroso methylurea. Again, these compounds unfortunately have also the side effect that they are strong alkylating agents, so they are also quite toxic. So you can already see that diazomethane is not a unproblematic chemical to prepare, but then also to handle. The way, the same thing, this is also hydrolyzed this base. And the way these type of reactions are believed to work, let me provide a mechanism here. And it's not completely clear, but it looks like there are a number of features which are logic to draw here in the mechanism. What is believed here is that you have a rather unusual way of using this tosyl group as a leaving group, and that it takes the electron pair with it. So if I want to draw this and to make this mechanism more plausible, potentially the base here is assisting or could be assisting this. Which then generates an intermediate like this, and I have let the oxygen here pick up a proton, which can come from water, and then another equivalent of base will eliminate, again, overall water here. So let's see that we are not getting confused here with the free electron pairs. To generate this structure, and then if I want to draw the other resonance structures of this, in the more typical way as it is drawn, you arrive at the diazomethane here. So much more commonly, derivatives of diazomethane are used, and derivatives which have an electron withdrawing group here, because then you delocalize the negative charge here. And so very typical are compounds which have an additional ester group here. So for example, ethyl diazoacetate, and this is quite easily prepared also on very good scales, on very good scale, by using the hydrochloride of glycine ethyl ester. Readily available from natural source glycine in large scales. And then what you typically do is you do the very same thing as you know from aromatic diazotation chemistry when you make azo dyes, for example, or diazonium salts. You simply treat this with sodium nitrite. In water and in organic solvents such as diethyl ether or dichloromethane, and you have some kind of a still buffer salt in there. And then in the very same way as you would formulate this on the, as you know this, on the aromatic compounds, you actually generate the diazoester, and probably many of you in the advanced lab course or so, if you work in my group or so, will do this because we prepare this actually all the time. So that's very reliable. And also, ethyl diazoacetate is commercially available even, and it's much more stable. You need to have a suitable metal, and I will show you the metals which decompose these ethyl diazo compounds, present. If you simply heat it thermally, it will not decompose. So you can actually distill it, distill ethyl diazoacetate. Nevertheless, since you can never be completely sure if some metals also are present, I also here would strongly suggest that you caution. We never distill it. We keep it as a solution with the organic solvent. But in comparison to diazomethane, ethyl diazoacetate is a lot more stable. Now, if you have one electron withdrawing group which can stabilize this anionic center here, obviously if you have two, this will even stabilize the diazo compound more. And so a third type of diazo compounds which are quite commonly found are diazo compounds which are derived from beta ketoesters. And these are so stable that only very few metals even will be able to decompose these compounds. A lot of metals which will decompose ethyl diazoacetate or diazomethane readily will leave such azo compounds of beta ketoesters completely untouched. There's also a very simple way to prepare these. You prepare these from the beta ketoester, which you know you can make by Claisen ester condensations or other ways. And then there's a reagent you should take note of, which is a very good diazo transfer reagent, and this is tosyl azide. And in the presence of a base such as triethylamine, a diazo group is readily transferred and you form these type of complexes. Let me also draw a mechanism for this. So under the basic conditions, you can formulate your beta ketoester in its enol form or also in its enolate if you want to deprotonate it here. So that becomes a good nucleophile. Tosyl azide then can be attacked on this nitrogen. To create an intermediate of this type. And now if we have our base present here, proton abstraction can occur. This can move in and being eliminated. And obviously this here can pick up protons from the aqueous solvent. Which then will lead to your tosylamine and the diazo compound. And again, that's a very good reaction you can prepare. It's an organic synthesis prep, tosyl azide from tosyl chloride and sodium azide in large quantities. It's stable. And the reaction is extremely simple. You mix them with triethylamine, you get this. This compound is completely stable. You can chromatograph it and very easily isolate it. Okay, let's look at some reactions. And let's start with reactions of diazomethane. Now, diazomethane is not stable against acids, and that is something you can use. It's an excellent reagent to It's not how I wanted to do this. So here we have another resonance structure which can also show that you can, in principle, write a resonance structure where you even have a positive charge here. And so nucleophiles are also able to react with diazomethane here. Did I do this right here? I'm not quite so happy how I did this here. Okay. So let's start this over. So diazomethane is not very stable against acids. You can use that as an advantage. Treating carboxylic acids with diazomethane is a very good and mild way to do an esterification with carboxylic acids. So protonation basically from the carboxylic acid on that carbon, and then nucleophilic attack under extrusion of nitrogen. Let me draw a plausible intermediate here. Where I have now protonated the diazomethane and now nucleophilic attack with nitrogen as a leaving group can occur to result in methyl esters. This is especially valuable if you are having a complicated natural product synthesis with a lot of functional groups which might not be tolerant against the normal way you would do this, doing an esterification by acidic acid-catalyzed reactions with an alcohol, or if you don't want to go first to activate this carboxylic acid. So simply mixing these two will very easily, with no byproducts, result in the methyl ester. Another reaction which is known as the Arndt-Eistad homologation, makes use of the anionic properties of diazomethane. So diazomethane readily will react with acid chlorides. Acting as a nucleophile. To create diazoketones. And such diazoketones now let me draw this out here. And such diazoketones, if you either heat them up or photochemically, or especially if you use silver 1 salts, then you will evoke the nitrogen extrusion here. And you can formulate such a carbene intermediate Okay, something is not right here as well. Because we add here this is still the this will be heavy editing here. So here in the moment we would still have formed a carbocation. So after attack of diazomethane to the acid chloride, intermediate of this type is forming, which will now rapidly lose a proton in order to form a diazoketone. To form basically what happens here is simply a substitution or substituted diazo compound is being formed here. And now if you treat these diazoketones either photochemically or better or more commonly used with silver 1 salts, the nitrogen extrusion will take place. And you can formulate, although it probably will not really occur as an intermediate, you can formulate such an acyl carbene and as seen so often, whenever you create a carbon center or also oxygen nitrogen centers which has 6 electrons, these type of species can stabilize itself by having an adjacent group migrating to it. So similar as you have seen 1,2 shifts of carbocations, also here in this carbene, stabilization can occur if this R group is migrating. And then this electron pair goes in. And so this way you create a ketene as an intermediate. Now this nitrogen extrusion and migration of the R group probably occurs simultaneously. So the free acyl carbene is most likely not even present. However, I have written it stepwise here to better show the mechanism. And these ketenes have now a number of ways to react further, and this depends in what kind of solvent you do your reaction. If you do it in water, then simple addition of water will occur, and you form overall the carboxylic acid here. And as you can see now from your starting material, which was the acid chloride here, overall you have inserted the carbene, which came out, the carbene equivalent, which came out from the from your diazomethane. You have inserted it between your R group here and the carboxylic acid, and what you have done is you have homologated by one CH2 unit your carboxylic acid. If you do this in an alcoholic solvent, you will form right away esters. And also very valuable if you do it in a non-nucleophilic solvent, in the presence then of an amine, you can actually form directly the carboxylic amide. And so you can use this type of chemistry for the homologation of alpha amino acids So if you take a protected amino acid, you activate it on the carboxylic acid function. This activation in peptide chemistry can be done, for example, with carbodiamides, DCC, common reagent, but again, you can also activate it even as an acid chloride. Treat it with diazomethane, then in the rearrangement, this group here will migrate. Now note that we have a stereocenter here, and of course you're interested in the fact that there's no erosion of stereochemistry, but indeed this takes place. So when this group is migrating, from this point to this point here, then the configuration here is retained. So the migration occurs with retention of configuration. And now again, if you treat this, for example, right away with an amine, which can be another amino acid, you actually are able to to form a peptide here where you have homologated the alpha amino acid to the beta amino acid. So this part here now is a beta amino acid. And currently there is a lot of excitement about replacing alpha amino acids in peptides with beta amino acids, because this way these peptides become stable. Usually an alpha peptide, a peptide which consists of alpha amino acids, you cannot use as a drug. If you take a pill which is a peptide, your proteases in your body will immediately cleave it and degrade it. The beta peptides are not recognized by the proteases, so the compounds become much more stable. And so there's a big hope now that you can develop peptidic drugs by replacing alpha amino acids in natural sequences with beta amino acids. And it has been shown that the functions very often stay the same or are even improved. So that's a quite important application here of that homologation type reaction. And we also already looked at the structure of diazomethane, that it is potentially a 1,3 dipole. And so therefore, it can undergo cycloadditions. With alkenes. And this also quite readily occurs. In this manner. In this way, you form such cycloadducts. Very often under heating, you can now extrude nitrogen and form cyclopropanes this way. But you will see that typically cyclopropanations can be more effectively carried out when you start with diazo compounds in the presence of metals. So therefore, let's look a little bit what can be done in the area of metal catalyzed. Cyclopropanations. And with a lot of quite a large variety of different metals, diazo compounds are decomposed under extrusion of nitrogen, but this happens in a much more, let's say, civilized way. And it is proposed that in the presence of metals, you will form, again, something which we have seen when we talked about metathesis reaction or Fischer carbines or Schrock carbines complexes, again, you will form such carbene complexes with an appropriate metal. And these carbene complexes, among other reactions, can be trapped with alkenes in order to form cyclopropanes. If you now look at the different diazo compounds which we had introduced so far, there is actually quite a difference in what kind of metal you will use. If you use simple diazomethane, the metal of choice which has been found to decompose it efficiently but mild enough so that it's not going explosively, is palladium 2 salts, palladium chloride. And this will very nicely result in a cyclopropanated product and again, it's important to note here that all these cyclopropanations are stereospecific. Which means that if I could count correctly, which means that the alkene geometry is retained in the complex and in the cyclopropane here. This might tell us something about the mechanism. This might tell us that it might not be a stepwise mechanism. We can propose, let me do this here, but leave some more room in your notes for putting on 2 more reactions down here. If we want to formulate a mechanism between an alkene and such a metal carbene complex, we can actually use what we have done before already quite often. We can propose that such a cycloaddition might take place and note here that this is also an oxidation of your metal. If this has, for example, with no further anionic ligands or so, let me propose that this has an oxidation state of 0 here in the moment with this carbene fragment. And the oxidation state here is +2 formally after the rearrangement because the carbene is considered as a neutral ligand, while now we're having 2 alkyl groups here which are considered as 2 anionic ligands. And then we have seen that with certain metals such as ruthenium, the metathesis reaction takes place in that a new alkene and another metal carbene complexes are formed. But with other metals, such as palladium, and we will also see copper and rhodium, palladium 2 to be more specific, copper 1 and rhodium 2, simply reductive elimination might take place. And then under regenerating the catalyst, with concurrent cyclopropane formation. And again, it's very dependent on the type of metal if such a formal reductive elimination or another metathesis reaction will take place. There are other proposals for these metals in the literature that these reactions go stepwise and that they do not go by such a cycloaddition mechanism. To simply grasp this overall picture, I like this. I like the analogy to arrive at one common intermediate here than to go to the two different type of products. However, especially for these cyclopropanations, this mechanism is not supported because nobody has so far been able to then isolate or characterize these metallocyclobutenes, but it's also not being disproved. And this type of mechanism, of course, explains nicely that the reaction is stereospecific because there are no open chain intermediates where rotation of the double bond geometry could take place. So if you go to the more stabilized diazo compounds, such as the ethyl diazoacetates, palladium 0 is not reactive enough. But what has been found is that copper 1 especially, but at the same time rhodium 2 can also be used here. However, copper 1 for this purpose is probably the most attractive catalyst because copper, of course, is a lot less expensive than rhodium. And so especially for large-scale applications, this is attractive. And again, the same type of cyclopropanation takes place easily. This time having an ester group in here. And then finally, if you go to the even more stabilized compounds with another acyl group here stabilizing the diazocarbon center, then you have to go to rhodium catalysts. Rhodium 2 is the only metal which will decompose these ones. These diazo beta-keto esters are more or less inert against copper 1. But rhodium 2, and again, all these reactions readily take place at room temperature in all cases. Cyclopropanation will then occur. To form these type of adducts. Now, in the handouts, I have given you some more examples, and especially I have given you, just so that you see this without that we are going into this or that we want to take applications out of this. But the one thing I would like to point out is that if you have ligands here which stabilize further the metal compound, if these ligands are chiral, then you can do these type of cyclopropanations in an enantioselective way. And you see that in these cyclopropane compounds, lots of stereocenters are occurring, and it is now possible to very efficiently control not only the relative stereochemistry, and we said the reaction is stereospecific, so your alkene geometry is retained in the products here, but also that the absolute stereochemistry of these carbon centers is being controlled. And there are a number of applications using these type of cyclopropanes as intermediates, and so therefore in like natural product synthesis. And I have also given you a few examples in the handouts of this. So there's important to control absolute stereochemistry. But the cyclopropane is also a very popular constituent in drugs. And very often drugs have been improved when alkyl groups have been exchanged for cyclopropyl groups. And so therefore also simply having cyclopropane rings in drugs is often very beneficial. Ciprofloxacin, for example, the very famous antibiotic from Bayer company, this has, for example, a cyclopropane, and it's done on huge scale. It's being produced on huge scale. Now, the one thing I would like to point out very briefly here is on the catalyst. So copper 1 is very common in, you find many copper 1 catalysts. The one which has been, the one salt, which is being used a lot, are the triflate salts. So the salt from trifluorosulfonic acid gives a copper 1 source which has a very labile ligand, so it can be displaced easily by other ligands such as chiral ligands here, and then also very easily the substrates will react with this. This is a very good source as a copper 1 salt. And rhodium 2 is also, there's also one complex readily available. However, rhodium 2 being D7, you can see it has an uneven number of d electrons, suggests, and that is the case, that rhodium 2 complexes are usually dimeric. And so the one very well-known rhodium 2 complex is the dirhodium tetraacetate, which has a structure where the acetate groups are bridging the two rhodium metals. And now this rhodium here has a total of 16 electrons. It's a 16 electron complex, and a carbene fragment can very nicely coordinate now in these axial type positions. And so therefore these type of complexes are ideally suited to form such metal carbene complexes, which then are very effective in these type of cyclopropanation reactions. The other thing you might appreciate is that if acetate is a good ligand, if you exchange acetate for a chiral carboxylic acid, you can quite easily make chiral complexes of this kind. And so, for example, what has been used are amino acids for example, proline derivatives which can be easily displaced. These proline derivatives can easily displace the acetate groups here, and this way you can create chiral rhodium carboxylic acid complexes. And I've given you quite a number of examples, again, just so that you can look at this in the handout without that I want to go too much into detail on the chiral aspects of this type of chemistry, but just keep in mind that it is easily possible both making chiral copper 1 as well as making chiral rhodium 2 complexes, which then can be used in asymmetric reactions of these metal carbene type applications. Now, metal carbenes offer another type of reaction which is very important and might be actually more important if developments will continue on this. And I predict there will be a Nobel Prize, let's say, in roughly 10 years for this type of process that carbenes, but hopefully we will learn to do this with other intermediates as well, will allow you to do CH insertions. And CH insertions to functionalize simple, let's say, hydrocarbons. Let's think about a very simple process. What we usually do with something like methane, we burn methane to carbon dioxide and use it for heat. This is more or less all we can do. But for example, it would be very nice if you could do an oxygen insertion selective in the CH bond, but then stop it there and create methanol as a chemical, as a different type of fuel, and so on. One of the principal problems is, of course, that once you do the functionalization, your intermediate becomes more reactive than your starting material, and you keep oxidizing it until you finally form carbon dioxide. There have been some very great progresses in developing this type of reaction. About 10 years ago, there was a list of reactions, the 10 most important reactions to develop, and the conversion of methane to methanol. And of course, ideally, you would like to do this with simple oxygen, and again, some kind of a metal catalyst was named as one of the 10 most important processes to develop by chemistry. Now, carbenes are possible, and the one key metal which is allowing this is again the rhodium-2. So the rhodium-2 carbene complexes, besides that they can go cyclopropanation, they are also sufficiently active to activate CH bonds. And let's look at a mechanism, a plausible mechanism, how a CH insertion could occur of a compound where we have now a sigma CH bond. And one plausible reaction mechanism, again, we can use the metathesis type mechanism, which we have already seen. Now, instead of doing this with a double bond, we choose a mechanistic picture where we have a single bond involved here. And you can also see immediately that this is harder because a pi bond is a much weaker bond. A sigma bond is much stronger. So you can appreciate that probably it's not so easy to do this type of activation. So if I formulate such a metathesis step here, I would arrive at such an intermediate where now I have a metal fragment between with a hydrogen and a carbon fragment, which now can undergo a reductive elimination, eliminating my metal here. To give me this product. And what you can see here now, what we have accomplished is that we have inserted the carbene into the CH bond and have functionalized this way our hydrocarbon. And let me simply show you some examples how this works or how that process can be used. By far, you cannot use any type of these CH bonds. It has to be an activated CH bond. And so typically, activated CH bonds are benzylic, allylic, or also CH bonds which have somehow a heteroatom. Very often you see this with oxygen or nitrogen attached to it. These are sufficiently reactive if you have simple alkyl groups here. These bonds react much slower. So usually these are good. And then if you go down the line, tertiary CH bonds are still good. But then secondary and primary CH bonds are much less reactive in this type of process. So let's look at a few examples how this can be used. And such type of reactions let me draw the diazo ketone right away, can be used in quite elaborate syntheses. I have given you this example in the script, so you don't really need to draw the molecule if you don't want to. So for example, in a late synthesis of a very famous compound, a cyclization was attempted by h-insertion. And you can see in this case, we have quite a number of CHs present. We have secondary CHs, we have tertiary CHs. And then moreover, if the cyclization takes place, you have to look at the ring size you might be forming. And although, and I show you an example for this also in a second, typically these type of CH insertions go through early transition states. And because there are early transition states, ring strain is not really such an important factor. Nevertheless, such insertion reactions occur especially well in the formation of 5-membered rings. So treating this compound with the rhodium acetate, and in principle you can see how you would use such a strategy. You have such a compound, you have your carboxylic acid. You activate the carboxylic acid as the acid chloride, and then you treat it with diazomethane. This is the reaction I've shown you in the Arndt-Eisters reaction to make the diazoketone. And now, if you treat this with rhodium diacetate, the rhodium carbene complex will form, and it's capable to do CH activation. And in fact, it will do this over the tertiary and not the secondary carbons here. Here, we could also form a 5-membered ring, but the tertiary CH is much more activated for CH insertion. And so therefore, not in terribly good yields, but nevertheless the insertion product had been obtained. Forming this new bond here. And from this intermediate, and again you have the final structure in your handouts. There was only a very small step further to make morphine. You can clearly see that the strength of these type of insertion reactions to make such bridge ring systems and now to selectively functionalize a CH here in the presence of the many other CHs, there are certainly not a lot of reactions that can accomplish this. Let me see if I want to give this. So the preference for forming 5-membered rings is actually can be high enough to override can be sometimes large enough or big enough to override activative positions. Now here first is an example which is again very typical in these type of CH insertions where your prediction might be, or whether this reaction process should be good. So in this type of situation, you would have a benzoic CH for insertion, and you would also form a 5-membered ring. So this way, insertion takes place very easily. And this was used to construct also certain drug molecules, which I have shown you in the handouts, where you have now formed by insertion a new carbon-carbon single bond here, benzoic insertion, and at the same time 5-membered ring formation. However, that this does not always have to be the case. Is shown in the following two examples. Now, if we look at this substrate here, you would see that we have a benzoic position which should be activated for the formation of the for the CH insertion. However, this would give us a 6-membered ring. And this CH here, which does not look very activated here, would lead to the 5-membered ring. And indeed, again, in this case, the 5-membered ring is the one which is being formed here. And so again, we've been forming this bond here, and this makes it sometimes difficult to predict these type of reactions. And to give you an even more drastic example, this type of compound here, there are obviously some tertiary CH bonds here. Which, however, would only form a 4-membered ring. Now, in this case, we have a primary CH this could form a 5-membered ring as well. And what is indeed observed here is that with very high preference, you actually form the 4-membered ring here. And again, it shows that in this case, activation is more important than ring size. Here we had ring size was more important than the activation. But also this example shows to you that apparently even strained rings, like this 4-membered rings, are formed, which points, as I said already, points to early transition states so that the ring strain is not really severe. So here with about 9:1, we had the insertion into the tertiary. So if I call this A and this B, we had the insertion into the tertiary CH, which leads to A, rather than in the primary one, which leads to B. Note here that in this case we are forming a beta-lactam ring. Beta-lactams is the principles in penicillin alkaloids, and actually quite a number of syntheses exist now where the penicillin or the beta-lactam bicycle found in these antibiotics is being prepared in this way. Okay, so with this, I would like to finish this. I would urge you to look a little bit at the handouts, because there you have examples with more complex molecules which I could not show you here. Now, before you leave, don't leave. We have there will be a young lady will be introducing a project about chemistry, learning, and understanding, and she can explain that better. What is the problem in learning chemistry? I think it's the bottom line here, and she will ask you to fill out a questionnaire, and please participate in this. I think it's a very important effort, and so the floor is yours. You can explain your project. Thank you.